Today we will start our next chapter, damped simple harmonic motion. So chapter number 2, that is damped simple harmonic motion. In the previous chapter we have studied only undamped or simple harmonic motion. Now it is damped simple harmonic motion. So what is the word? The meaning of this word damped. Damping means decreasing with time. So if we compare the undamped and damped motion SHM, then we will note that this is the graph which represent undamped and damped. This one, this is called undamped oscillator, and this is damped. So we can say that the oscillations are said to be damped if its amplitude is decreasing, this one decreasing, amplitude is decreasing with the time. And in case of undamped oscillator, the oscillations in which amplitude of the wave remain constant throughout the whole period. So this is damped, this one is undamped. So in the previous chapter we have discussed this type of motion, that is undamped motion, but in this chapter I will discuss damped simple harmonic motion, or this second one, this is damped. So damped means damping. So we can define the motion is said to be damped simple harmonic motion if the amplitude of the wave is decreasing with the increase in time. This is damped oscillator. So what is the factor which is responsible for this damping? So that factor is called damped force. Damped force. So damped force is responsible for decrease in amplitude, and this type of force, let that force is written by small f, and this force is directly proportional to the rate of change of displacement, or we can say that the force is directly proportional to velocity. And if we solve this proportionality constant, there will be minus r into dx by dt. So this minus sign is used only for the restoring force, because this force is acting in the reverse direction to the applied force. So it is negative force, and this r is called proportionality constant, proportionality constant, or damping constant, damping constant. So this new type of force, so I think we have not read or studied this force which depend on velocity. We have already observed or studied so many formulae for velocity, for force, but this is a new formula in which the force depend on velocity, the rate of change of velocity. So it is minus r into dx upon dt. So this is damping force. So in this chapter we will discuss again damped mechanical harmonic oscillator and damped electrical harmonic oscillator. So there are two further parts. First one is damped mechanical oscillator, and second one is damped electrical oscillator. So, mechanical and electrical. And then we will find the physical factors or physical variables which determine the dampness or this damping. The factors or physical parameters which are responsible to describe the damped oscillations. So, these factors or these parameters, third one, the parameters which describe the damping are called damping parameters. Simply, in simple words, we can say that these are damping parameters. So, this is our whole chapter. That is, first of all, I will discuss damped mechanical oscillator, and after that damped electrical oscillator, and then the parameters or damping parameters we will study in detail. So, first one, damped mechanical oscillator. So, we can consider the same example, that is spring mass system, that is SM system, spring mass system, so which we have already discussed in undamped oscillator. The same type of example will be discussed in this case. So, let a spring, this one spring, and a mass is attached to the spring. Both are lying on the fixed support or table, this is table. When we apply force on this side, this is called applied force, force 1, applied force. Then this mass will reaches at this position on applying force. But when we release that force, this mass will automatically came back in the reverse direction. So, that reverse direction, the force is called the force produced by spring or restoring force, second one. So, F1 is applied force and F2 is called restoring force. If you consider the damping factor in this case, then a new or additional force F3 is also applicable on this system, which is due to air friction. So, that F3 is called damping force, or it also called frictional force or air friction. So, it may be any type of force which produce the damping or which decrease the amplitude of the oscillations. So, there are three forces, F1, F2, F3. In the previous article, we have used only two forces, that is applied force as well as a restoring force. But in this case, additional force F3, that is damping force, is also added in this equation. So, in all cases, first of all, we will derive the equation of motion for mechanical oscillator or damped oscillator, and then we will solve that equation in detail and find out the different possibilities of damping. So, to find differential equation of motion, we will derive equation of motion. So, similarly, we will follow the same steps as we studied in the previous articles, that is deforming force or applied force. F1 is deforming or applied force. Applied force. This force is nothing. This is m into a. So, F1 is m into a, which is m into d square x upon dt square. First one, force. And second force, F2 is restoring force which is minus S into X, because this force is according to Hooke's law, because it is applied by the spring in the reverse direction. So, minus sign shows the reverse direction, and S is stiffness of the spring, stiffness constant, X is the displacement. So, this is Hooke's law. So, this force is, we have already used in previous article, that is Hooke's law, restoring force. But in this case, a third force is also applicable, F3, that is damping force. Damping force. So, it is nothing, it is minus R into dx upon dt. This one is third force. So, this force is already discussed. So, there are three forces, first, second and third. Two forces are negative in nature because they are restoring forces, F2 and F3, and F1 is positive, that is deforming force. So, the equation of motion for this oscillator become by using these forces. So, net, the resultant of these three forces is equal to F1 is equal to F2 plus F3, that is deforming force is equal to restoring force or forces. So, deforming force is single and restoring forces are double, two forces are restoring. So, deforming forces are written on left hand side and restoring forces are written on right hand side. So, this is the equation, this is the equation. So, F1 is m into d square x upon dt square is equal to F2 is minus Sx and F3 is minus R dx upon dt. So, this is the equation for damped oscillator. You may write in a simple way this m into d square x upon dt square plus R into dx by dt plus Sx is equal to 0. So, this is the equation and it is second order differential equation which represents the equation of damped mechanical oscillator. So, in our next lecture we will find the solution of this equation and solve this equation in detail and find the different possibilities of damping. Thank you very much.